Dear students, welcome to the course of VLSI Circuits and Systems. Today's topic, ZPU by ZPD ratio for an nMOS inverter driven through one or more pass transistors. Whereas in the previous topic, we have derived the ZPU by ZPD ratio for an nMOS driven by another nMOS inverter. Now, whereas we are going to consider the same ZPU by ZPD ratio for an nMOS inverter driven through one or more pass transistors. Right? Let us go into the details. After completion of this lecture, you will be able to derive the pull-up to pull-down ratio for an nMOS inverter driven through one or more pass transistors, and you will be able to examine the other alternative forms of pull-up. What is meant by a pass transistor? So, taking into consideration the figure here, see, we have three nMOS transistors. This is N1, N2 and N3, driven with the inputs A, B and C respectively at their gates, and one end of the circuit is connected with VDD voltage, and other end of the circuit is X, that is how much amount of voltage will be reached to the other end of the circuit. So unlike bipolar transistors, the isolated nature of the gate allows MOS transistors to be used as switches in series with lines carrying logical levels in a way that is similar to the use of relay contacts. That is, see, unlike in BJT, what here this happens is the isolated nature of the gate, isolated gate, IGFET we call it as MOSFET otherwise, isolated gate, field effect transistor. The gate allows what? To be connected, the switches nMOS, this is one switch and this is the other switch. This connection is known as a series connection, which also is similar to the use of a relay. So whatever the signal you apply here, if this switch is on, that will be transferred here, and if this switch is on, the same should be transferred here. So this phenomena is called as a pass transistor phenomena. Pass transistor is not a new transistor, it is again an nMOS connected in series switches. The application of the MOS device is called the pass transistor. This application we call it as a pass transistor application. Switching logic arrays can be formed, for example, an AND array as in figure. So this figure forms an AND array, that is when all the devices inputs are logical ones, then only the input of the circuit will be transferred to the output. That is what an AND array representation. Now let us consider, so now that's with the pass transistor. Now entering into your topic, that is a pull-up to pull-down ratio for an nMOS inverter driven through one or more pass transistors. See here, this is an nMOS inverter, not driven directly by an nMOS inverter. Instead, in between there are pass transistors, a set of pass transistors. Let us consider. So consider this arrangement of inverter 2. The input to inverter 2 comes from the output of inverter 1, but passes through one or more nMOS transistors used as switches in series called a pass transistor. So connection of pass transistors in series will degrade the logic 1 level into inverter 2 so that the output will not be a proper logic 0 level. See, connection of pass transistors here in between inverter 1 and inverter 2, what happens? Let us consider a logic 1 level is there at the output of inverter 1. This will not be a perfect, proper logic 1 at the input of inverter 2 because this gets degraded by this connection. So if this is VDD, this gets degraded by an amount of, that means the remaining amount is VDD minus VTP, where VTP is the pass transistor voltage, we may call it as. So because of that one, your output may not be a logical 0 properly. The critical condition is when point A is at 0 volts and B is at VDD. So for A with logical 1 and B with logical 0, there will not be a much problem. But the point A, if it is at logical 0 and point B definitely will be at logical 1, then this logical 1 will be degraded as VDD minus VTP here. Then arises the problem. That is what we call this as a critical condition, this condition. But the voltage into inverter 2 at point C, that is point C is here, that is what we have discussed, now is reduced from VDD by threshold voltage of the series pass transistors. How much? That is VTP. So with all pass transistors gets connected to VDD, there is a loss of VTP. Therefore, V into is given by VDD minus VTP, this one, where VTP is the threshold voltage for a pass transistor. We must now ensure for this input voltage, we get out the same voltage as would be the case of inverter 1 driven with input VDD. So now what is our thing is, for this input, the output should be what output we'll get for an inverter 1 if we apply VDD as the input. The same output I should get even the input is VDD minus VTP for inverter 2. So that one, what should be the pull up to pull down ratio, right? Now consider inverter 1. See here the circuit are taken differently, where it is represented like this. So when we are considering our inverter 1, so you know what is the pull up network and pull down network. Pull up network is a depletion mode transistor, and pull down network will be an enhancement mode transistor. Here the output will be taken, here we connect the input. Now consider this as inverter 1. So in inverter 1 with input as VDD, let us say our input is VDD. Now see, if the input is at VDD, then pull down transistor T2 is conducting but with a low voltage across it. Therefore, it is in resistive region represented by R1 in the figure. So now see, the enhancement mode transistor, when you apply VDD, it will be conducting, the transistor will be conducting, but with a low voltage across this. Low voltage means that can be represented with a resistance R1, and voltage across this one is V out 1. This is enhancement mode transistor. That is what this representation. Meanwhile, the pull-up transistor T1 is in saturation. So we know always this will be in saturation. Why? Because VGS is equal to 0 will make depletion mode transistor to go into saturation always. And it is represented as a current source. A saturation transistor is represented with a current source, and a current of I1 is being flown through this depletion mode transistor. So now for the pull down transistor, let us consider this is a pull down transistor, this one. IDS is given by, so as I mentioned, this is conducting and this could be in linear region. So this is the equation we know already, K into W by L into VGS minus VT minus VDS into VGS minus VT into VD minus VDS by 2 into VDS. So as this, that is pull down, W by L will change to WPD1 by LPD1. VGS minus VT is, VGS is VDD we have considered, so that is there. VDS is drawn inside here, that is VDS1 minus VDS1 square by 2. Hope that is clear. So from this equation, if I want the resistance offered by this transistor R1, we know the formula VDS1 by IDS. So from this equation, if you derive VDS1 by IDS, we'll be getting it as 1 by K into LPD1 by WPD1 divided by 1 by VDD minus VT minus VDS1 by 2. So now as VDS1 is itself is small, so as you have mentioned, the pull down transistor is conducting but with a very low voltage across it. Low voltage means that is VDS. So VDS is itself is small. So compared to VDS, VDS1 by 2 may be ignored. So this equation changes to this equation, this VDS1 by 2 gets ignored. Now for depletion mode, that is pull up, that is in saturation, for VGS is equal to 0, the current flowing I1, this we have seen on our previous topic, K into WPU1 by LPU1 minus VTD whole square by 2, that's okay. So the product I1 R1 gives our output voltage. So what is output voltage of this device? The same current will flow through both the devices. So what is the voltage across R1 is I1 R1, basic equation. So now using this I1 and using this R1, you will be getting the Vout1. Hope that is clear. Now consider our inverter 2. So similarly, this inverter 2, this circuit is acceptable to you based on the previous slide explanation. Now for inverter 2, the input will not be VDD. We need to consider it as VDD minus VTP as far as our discussion is considered. So as derived previously, for inverter 1 we have derived R1. No? Now similarly R2 will be what? The same equation, but in place of VDD we will be having VDD minus VTP. And whereas I2 will be identical or most similar equation we are going to get. So based on this one, what will be the Vout2 of this circuit? So of this circuit, what is Vi2? Vout2 I2 into R2. So product of these two will result in Vout2. So what is our intention? With an input of VDD or with an input of VDD minus VTP, both the output voltages should be same. For that one, what should be the condition? So that represents I1 R1 is equal to I2 R2. Substituting these two equations here, so that results in ZPU2 by ZPD2 will be equal to ZPU1 by ZPD1 into VDD minus VT by VDD minus VTP minus VT. Substituting all the typical values, Vt is equal to 0.2 VDD, pass transistor threshold voltage put together is 0.3 VDD. Substituting in them in this equation, we get the ZPU by ZPD ratio will be 2 times the ZPU 1 by ZPD1 ratio, that represents 8 by 1. So ZPU 2 by ZPD 2 is divided by ZPU 1 by ZPU 2 will be 8 by 1. So the pass transistors, because of the pass transistor, the ratio has been changed as 8 by 1 instead of 4 by 1. Looking to few alternative forms of pull-up. So for our device, the pull-up previously what we have seen is a depletion mode, but there are 4 types of pull-up. Load resistance pull-up, nMOS depletion mode, that is what we have seen, nMOS enhancement mode, and complementary transistor pull-up. In short, we call it as CMOS. Looking into the details, this low transistor pull-up this resistor occupies a large area, so this is not commonly used. Whereas nMOS depletion mode, till now what we have discussed, will dissipate more power since rail to rail current flows when logical 1 is given. So when input is logical 1, the current flows from supply rail to ground rail. And also switching of output from 1 to 0 begins when Vin exceeds Vt of the pull down device. See here, output will not switch from 1 to 0 immediately. Instead, it will be taking certain amount of voltage known as threshold voltage of this transistor. And when switching the output from 1 to 0, the pull-up device may present lower resistance through which the charge capacitive loads. So when we consider a stray capacitance here, so when switching from 1 to 0, actually this would become 0, but because of the less resistance path here, this capacitance may charge towards the supply. And whereas if you replace the pull-up with enhancement mode instead of depletion mode, so VGG, this should be VDD in order to always switch on this. So in this case also, when input is 1, the current flows from supply to the ground, rail to rail current flows, that dissipation is high. Whereas Vout can never reach VDD. Why? Vout will always be VDD minus this VTP, we call it as, that is pass transistor analysis. That is what output will always be a VT voltage less than VD. Whereas complementary modes, this need to be elaborately discussed in our next topic. We'll solve all these disadvantages. There is no current flowing either from logical 0 or logical 1. Full logic 1 and 0 levels will be at the outputs. Why? Because if this is on, this will be off, and vice versa for any input you are going to apply. and these would be the characteristics, and this is the current being flown.